Hello everyone. Today we'll be discussing our latest technical paper, Overcoming Multiple Caverns, Successful TBM Tunneling in Karst Geology at Galerie des Janots. Our speaker today is Detlef Jordan, Robin's Sales Manager Europe. My name is Desiree Willis, Robin's Public Relations Manager, and I'll be moderating today's presentation, which will be formatted as a question and answer session. Let's get started. Detlef, can you tell me a little bit about the Galerie des Janots project and what the most interesting aspects of it are?
Yes, for sure, Desiree. Thank you so much for giving me the chance to talk to you and the audience today about this challenging project. Let me give you some insight into this project first, some general insight. The Janots project was planned for a long time. In fact, it was interrupted a couple of times due to some objections of residents and community in that area. The purpose of the project was to build a new water supply line in parallel to the existing one, which was built back in 1956, 1964. And the capacity of this water supply line is limited to about 300 liters of water per second flow of water. And this line had to be replaced. It's because it's one of the most important water supply lines in that area of Marseille, and people need water in summertime because it's a very hot area. So it was a must to replace this line. The alignment for this new bored tunnel that was selected to do is in parallel to the existing railway tunnel line, and it's under crossing a national park. As I said before, it's very nearby to residence areas, so people are very sensitive in the area. What happens in that let's say in the front of their houses, so you can imagine that people had objections at times. But in the end of the day, the owner succeeded, made it happen, to build this tunnel. The tunnel is in rock formations of limestone with karstic formations, which is quite normal in this area. When you go to the southern European area, you find karst very often. The owner had the choices to either go drill and blast or make it by TBM. And the owner decided to define a TBM operation. Last not least, because the TBM operation is more smooth to the rock, it treats the rock more sensible than a drill and blast shooting, as everybody can imagine. So the successful contractor, which was French Eiffage, approached the industry and approached us to offer a TBM for this project. And that's what we did. We selected an open type TBM for the excavation of this water tunnel. That's a little bit about the condition, how it came to this project, and the general terms. You will find on that slides, on slide number 2 and slide number 3, a little bit of a listing of the main data of this project. So we're speaking about the 3.5 meter diameter TBM. The tunnel was 2.8 kilometer in length, and it was completed in 2019, so not that long ago. And as I said before, geologically it was limestone and everything underneath this national park, which is a very sensitive area in this region.
Great. And Detlef, you mentioned karst geology. Can you explain a little bit more about karst and the challenges of tunneling through those formations?
For sure. What is karst? You know, karst is a phenomenon that you find, as I said before, very often in the southern European area. Rock down here is often from limestone. And when this limestone, let's say, gets in touch with water, the limestone becomes very weak. And in consequence, the limestone gets solved in the water, so it's a loss of volume in the rock. And the consequence of this loss of volume is you leave fractures behind, the whole rock mass is weakened, and in consequence you get sediments on the surface and, let's say, disturbation of the rock mass. So it's a very serious thing. And you know, let's say the evolution of the last thousands of years in the geology provided all these rock mass disturbations of karst. So karst is found quite often, specifically in this area. What can you do when you run into the karst? So you have to deal with very unstable and weak rock formations, and you have to control this. So you have to stabilize. You have to inject, you have to take care for water ingress, you have to inject the rock to make it stable, support it, not to run into a complete phase collapse, because what happens is a settlement, let's say development that runs to the surface, and this in most of the cases is a clear no-no in the projects. You cannot have settlements. That is what owners are very, very alert about. So you have to take this with highest attention and do something against it. The technology in TBM operation is very, very high advanced in these years. So you find all these means and measures and technical devices to look ahead of the ball, because looking ahead is one of the most important things when you come in such ground formations. And so you can do it by conventional probing, just drilling ahead, reading the data. And you can also get these, what we call measurement by drilling systems. These are systems that read all the data from the TBM operation, and they analyze the data and give you an idea about what is to expect. You can expect what comes ahead of you. So you will have a very good, let's say, prospect when you employ these things, what you are running into. So I would say these features are not something nice to have. It is sort of a must, meanwhile, on TBMs when you're running such disturbed formations. And you can see also on the slides here on the fourth and the fifth slide a bit of the Karst phenomenon. It's in keywords what I explained with my explanations. It's when you come into Karst, you have to deal with high water ingress. It's a loss of ground, it's sediments, and you have to take it very serious.
And Detlef, can you tell me a little bit more about the TBM design and how it was designed for those ground conditions?
Yeah, absolutely. You know, the TBM, the selected TBM, is an open type main beam machine. Say kind of a hard rock tunnel boring machine. So there is a small shield in front of the machine next to the cutter head, but not a full shield support. So people would say, oh my God, it's disturbed rock, so open type machine, wouldn't be better to go with the shielded machine? So my clear position on this is no, because when you're running into disturbed rock formations, the very important thing is you should see and communicate with the rock. That's what I usually say, talk to the rock. You know, it's also kind of a professional approach in tunneling. When you bore, let's say in some geological formations, if you bore a tunnel, you should not go in there, just bore the hole, put segments and leave behind uncontrolled what you have done. You disturb the geology in this area. You have to control what you're doing there. When you go with an open type machine, you can control what you're doing because you see the reaction of the rock. This is a very important feature in tunneling, to see the behavior of the rock and react. When you put segments, you can't react. Don't get me wrong, in some rock you have to go segments. When you go in very soft formations, then it's no way without segments, you have to go. When you go with an EPB machine or a slurry machine, you have to go with shielded machines, no doubt. But in this kind of formations where you have limestone, which is by nature stable, but you have some faults to expect, this is, let's say, then the classic, the professional way should be go with an open system, communicate, talk to rock, do something, stabilize the rock. And this is what an open type machine allows you to, because you see the tunnel walls. In this specific, let's say, tunnel, we had with Eiffage, a contractor on the job site, very, very, very experienced in this industry. And we have been on the same opinion, Eiffage and us, to select an open type main beam machine for this tunnel. So this is, let's say, the main feature. It's an open type machine, and when you look onto the slide, what the machine design, it gives you in the listing the main data of the machine, the key data, the installed power, all these features. You will find the power installed on the machine is not so high. So we're talking less than 1,000 kilowatts. Nowadays, in industry, people often say, oh, the more kilowatt on the head, the better. I don't share this, you know. You should have that much power on the machine that you need to employ. And very often when you run into formations, and limestone is not so very hard, and you have fractures, it's not a question of power, it's a question of sensitivity, question of smoothly operated machine. Run the machine evenly, don't overthrust, don't overload the rock with the machine. So this machine was the right choice for that. It was exactly fine, and the consumption of power was far away from the extreme.
And
Yeah.
Detlef, I understand the job site was quite small. How did that play a role in the TBM assembly and launch?
Yes, indeed. It was a very small job site. You know, the space available was very much limited. The job site was embedded into a small valley. On the one side, there was a road, a national road, a very busy national road, and the job site was next to this national road. Then they had to deal with the residential area. People have been living there in their houses, old houses, expensive houses. And last not least, we had the national park above us. So there have been factors limited the space available because it was not allowed to expand the job site and just, let's say, cut trees or something. That was absolutely not possible. It was very, very much limited to let's say, make a plan and make a site installation there. And in fact, we had to build the bridge, the contractor had to build the bridge to somehow provide, let's say, a connection between both sides of the road to allow access to the tunnel. So that was very, 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 let's say, limited in space there. So what we had to do, we had to assemble the machine in two stages. So the front and the rear. And what we did, the front of the machine, there was enough space to assemble the machine at the portal, the front part, and the first 5 gantries. That was enough. And the rest of the backup had to follow. So we had the first stage, front end, 5 gantries, and then the second stage. And we prepared the machine in such a way that all connections and all cables and what have you between the gantries of the machine had been by quick connection systems, so that we don't need to have to put wires on hardwire, and it takes too long time. So we had quick connections there to make it a very simple operation. That worked very, very well, I have to say. So it was not a big difference between an assembly where you roll up the machine in full. It was a good job that we all did there, let's say.
And what were some of the challenges the crew faced as they started tunneling?
Yeah. So once when the assembly was finished and we launched the machine in March 2017, and the crew has done the first kilometer, and then they run into the first cast in the cavern. It was in fact a huge cavern. They found the cavern in the 10 o'clock position, looking ahead of the drive, in the drive. The 10 o'clock position of the machine. It was, let's say, a very, very big cavern they found. And it was stable. Thanks God it was stable. So we have been able to enter into this cavern, to go into. It was marvelous to see this, really marvelous. I've never seen it before in my life, such let's say, such a cavern. And what they had to do, they had to fill the cavern. They had to fill it up, plug it, to provide support for the machine to go on. You know, before they ran into this cavern, the cavern came in the end. It cannot came without any announcement, because from the very beginning, the rock mass was weak and disturbed. So the very first 1,000 meters, the crew had to deal very often with, let's say, weak formations, lenses with clay stone that plugged up the cavern. So running into this cavity was, in the end, was a thing that we had to expect. It was clear something will come up here, but we didn't expect it to come so high, so big. The cavern was, I think, 8,000 cubic meters in size, so really, really huge. So besides all of the, let's say, this bit of an adventure to find something like this, it was critical, it was dangerous. But the people managed it very professional and very, very, let's say, quickly. So in about 2 weeks' time, we overcame this obstacle. It was really, really quick and sharp. So, and this included also, let's say, the baptism of the cavern. The cavern was named after the geotechnical engineer in charge, Marie Le Semblé. So she became the first good mother of a child, an underground child, more or less. But she won't see that again, I'm afraid, because it's filmed. So that was the first big, let's say, stop on the road.
And were there any other difficulties with ground conditions? What type of ground support were they using?
Yeah, you know, when speaking about the ground support a bit here in this time, it was an open type machine, so we had to install ground support. But you know, the need for ground support was, I would not say it was not by the book. It didn't came, let's say, regularly. So there's beams and things here. It came pretty much uncontrolled. So there have been sections where the people had to put beams and bolts and meshing and shotgun and everything, the full venue. And other sections, it was just a few bolts and fragments of a beam. So it was very much varying. And they made it very efficiently. They just put what the rock was asking for. Going back to what I said before, communicate to the rock. And they did very, very, very good and perfectly. So they gave to the rock what was needed. This made the whole thing still in a very efficient and fast drive. So it's in the end, it paid out to have an open-type machine to just put what was needed. You know, just to not forget our slides that people will see. So you see on these slides, here's a picture of this cavern that we ran into, and also you see the location of the cavern on the 10 o'clock side, the left-hand side of the machine. So the small picture gives a bit of an impression there of what we ran into, and also it shows what people did. Let's say to close the cavern, it was a concrete wall, but all this was done very professionally. And also on the other slide, you can see the ground support that I spoke about. The ground support, selective ground support, sometimes full beams. You can see on this one picture here all the beams there, and on the other side just some bolts and nothing like this. So pretty much selective ground support. But this was not the only cavern we found. So the people moved on, and the speed really went up after we closed the first cavern. And they made 400 meters a month, but it's really, really good performance for a machine of that size. Small machine, you have to deal with a small diameter, logistic, and a small tunnel. So they've been very, very fast. And then arriving at about 2 kilometers in the tunnel, all of a sudden, the next cavern showed up. And this was more difficult, even more dangerous than the first one, because this cavern was, we hit the cavern on the top side. So we have been in the top of the cavern. So the bottom, let's say underneath the bottom of the machine, there was nothing. There was open space. So it was a bit of luck also that nothing seriously happened, because when you run into something like this, you can easily lose the machine, because the machine starts diving, going down, and it's not very nice. So they stopped the machine. Then we had to find how to investigate what we have here. You know, when you have a big machine, you can easily cross by the cutter head to the front, but on a small machine, it's not so easy. So they did it to just make a further investigation and see what they had, and they found that the cavern was about 14 meters deep, so the whole machine would have fit in there. So to treat this cavity, there was need to make bypass tunnels. So what they did, they drove 6 bypass tunnels around the machine to just access and go to the front to fill it. And this cavity was filled with about 1,500 meters of concrete, just to get a solid support for, let's say, to go on, to bring support to go on board with the TBM. 1,500 cubes of concrete, that is about 250 trucks, mobile trucks of concrete. So you can get an impression about what happened on job site at the time. They poured concrete days and nights just to fill it, and that took some time, but still they managed it in a very professional way and filled it, and then they went on and finished the tunnel. Thanks God.
So given the experiences the crew had on this project, would you recommend what would you recommend for contractors boring in karst geology?
In general, Desiree, let me say that boring in karstic formation is not a miracle. It may sound it's dangerous and you have to be careful, but it's not a miracle. And with all the modern technologies that you have available on the tunnel bore machine, you can very well drill and bore in karstic formations. You should not forget one thing: when you have to do a tunnel in such formations and you have the choice, go TBM or drill and blast, still the TBM is the more soft instrument compared to drill and blast. Drill and blast gives you impact, shocks to the rock, and that is not good for karst at all. Not for good for any rock, but for karst specifically, for this type of rock mass, you should avoid that as much as possible. So the boring by TBM absolutely is the right way to go. Make it a smooth and easy going job. Don't push too hard. Don't exaggerate the thrust on the cutter head. You know, sometimes when people bore in limestone is not very hard, and the machine starts running and running, and people overpush, they put hard speed, 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 and all of a sudden run to a crack. Don't do that. Continuously. Go step by step, slowly. Take it easy. That is what I can tell people when coming to the formations. Don't overthrust the machine. Don't run too fast. Make it a very easy job. Take it nice and easy. That's really the important thing, specifically when running into such formations. That's my message to the people running into these projects.
And one last question, Detlef. What's the one most important thing that contractors can do to specifically prepare for karst?
Yeah, I would say it's not related to karst formations only in general. You should employ your machine with all these tools that are available to look ahead of the drive when you do tunneling with the tunnel boring machine. Assemble probe threading machines, assemble measurement while drilling systems, assemble the beam. The beam we saw on one slide briefly. A beam is a electrical system that looks ahead of the drive as well. Very nice systems, so they are available. Install them, but use them. You know, I don't want to be the wise guy here, but too many often I experience that the systems are there and people don't employ them. Why? Because they are afraid of stopping the machine, because when you want to employ this, sometimes you have to stop, interrupt the operation. But you should do that. It pays in the end of the day. Going ahead and running into trouble, then think about that's too late. That's too late now. So you should really, let's say, employ these tools. And when you run into a cavern, make sure you have a lady engineer on job site, that you have somebody for the baptism. That's a little bit of my message to the people that run into this.
Thanks, Detlef. This was a great session. And for our viewers, be sure to check out our other white paper recordings from 2020 trade shows. We'll be releasing them throughout the year on our website, therobinscompany.com.